All right, let's talk about one of the most buzzed about and honestly most misunderstood technologies out there, the blockchain. We're going to break it all down and actually build one from scratch right here, right now. And our building blocks, well, they're going to be office snacks. It's the only way to really get how this stuff works. So you ready? Let's dive in.
You know, it all really boils down to this one huge question. Think about it. In our digital world, hitting copy or delete is second nature. So easy. So how on earth do you build digital money that someone can't just cheat? How do you create something you can trust, where you can prove something happened and nobody, and I mean nobody, can go back and change the story? That's the puzzle we're tackling today.
So to really see why this is such a tough nut to crack, I want you to meet someone. Let's call her Lisa. Now, Lisa runs this little digital payment system at our office, basically for buying snacks. It's nothing fancy, just a cookie token spreadsheet that lives on her computer. Super simple, totally centralized, and as we're about to find out, really easy to cheat.
Okay, so picture this. One afternoon, Lisa's got a craving for a cookie, but she doesn't want to pay for it. So she walks up to the office cafe, sends over a cookie token, and makes a big show of recording the payment in her spreadsheet. Everything looks legit, the cafe hands over the cookie. But later that night, when no one's looking, she just opens up that file, finds the line item for her payment, and just hits delete. Poof, gone, like it never even happened.
So the next day, the cafe is counting up their tokens, and they notice they're short one. What can they do? I mean, they can go to Lisa and say, hey, you didn't pay, but she can just shrug and say, yes, I did, check the spreadsheet. The problem is, the only record, the single source of truth, is the file she controls, so it's their word against hers. And that's the fundamental flaw of any system like this. Without a record that can't be changed, you don't have truth, you just have an argument.
Well, Lisa's coworkers, they're pretty smart. And they figure out pretty quickly that the spreadsheet itself is the weak link. So they huddle up and decide to create a whole new system, a system that Lisa can't just secretly edit in the middle of the night. Their big idea? Let's replace that spreadsheet with a blockchain.
You know, at its core, a blockchain is pretty much what it sounds like. It's a chain of blocks. Each block is just a list of records, like transactions. But the real magic, the secret sauce, isn't just that they're connected. It's how they're connected. These links aren't just lines in a spreadsheet. They're forged with some seriously powerful math, cryptography, that makes them, for all intents and purposes, unbreakable.
All right, let's actually build this thing. So imagine the new cookie token system is live. And this, right here, is the latest block in the chain. We'll call it block 19. It's just a list of the most recent cookie and coffee purchases. It's the current end of the line for our new digital ledger.
Okay, so more people are buying snacks, which means it's time to add a new batch of transactions. That's where block 20 comes in. And here's where things get really clever. Block 20 doesn't just get tacked on. It actually contains a unique cryptographic fingerprint. Think of it like a digital DNA sample of block 19. This creates a powerful one-way link that points backwards, forever tying block 20 to its parent, block 19.
And this process just keeps on going. When block 21 comes along, it gets stamped with the fingerprint of block 20, which of course has the fingerprint of block 19, and on and on and on, all the way back to the very first transaction ever made. What you're building is this incredible chain of dependency. It's like each new block is another lock, making the entire chain that came before it even stronger.
So let's pop the hood for a second and see what's actually inside that finger part, or what we call the block header. It's got a few key ingredients. First, the ID of the block that came right before it. That's what makes it a chain. Then you've got this super condensed summary of all the transactions inside this block. Add a timestamp so we know when it happened. And finally, and this is super important, a digital signature from Lisa proving she's the one who created and approved this block.
Okay, so here's the absolute key takeaway. Because every single block is cryptographically tied to the one before it, you simply cannot go back and change something in the past without setting off a massive chain reaction. It's like a line of dominoes. If you try to alter block 19, the fingerprint in block 20 won't match anymore, and then block 21's won't match it. The entire chain from that point forward would instantly become invalid, and everyone on the network would see it clear as day.
All right, so our new system is looking pretty tough. It's way more secure than a simple spreadsheet. So let's go back to our crime scene. Lisa has just bought her cookie. The transaction is fresh. The question is, can she still pull off her heist?
So her cookie payment is officially recorded in the newest block, block 21. She's got the cookie in hand, and just like last time, she gets that little evil idea. I'm gonna erase the evidence. So what happens now? What happens when she tries to delete that single transaction from block 21?
And this is where it all falls apart for her. It's brilliant. See, to get rid of her payment, she can't just delete it. She has to create an entirely new, fake version of block 21. We'll call it block 21B. Since she removed a transaction, the summary of all the transactions inside, that Merkle root we talked about, is now different. It has to be. And to pass it off as real, she has to sign this new fraudulent block with her digital signature. But here's the smoking gun. Now there are two completely different versions of block 21 out there, and both of them have her signature on them. The cafe has the original, honest block 21, which clearly shows her payment and has her signature. But Lisa has just created and signed a second version, block 21B, that tells a completely different story. The argument is over before it even begins. They don't have to debate. They have cold, hard, cryptographic proof that she tried to cheat. It's like finding two signed confessions to two different stories. She is caught, absolutely red-handed.
So that's it, right? Problem solved. Lisa can't cheat the system anymore. Well, kind of. We've solved the security problem, but we've accidentally created a logistics problem. As this chain grows, with thousands and thousands of blocks being added, the whole thing gets huge. I mean, gigabytes and gigabytes of data. And trying to download all of that onto your phone just to check if you can afford a cookie? Yeah, that's not going to work.
And that brings us to the next big hurdle. How can something small, like a mobile wallet on your phone, verify a payment without needing to download the entire massive history of every transaction ever? We need a way to prove something is true without needing to see the whole story. We need a lightweight solution.
The answer to this problem is a really elegant cryptographic trick called a Merkle tree. Okay, stick with me here. It sounds complex, but the idea is simple. You take every single transaction in the block and you hash them in pairs. Then you take those results and you hash them in pairs. You just keep doing this over and over, all the way up the tree, until you're left with just one single tiny 32-byte hash. That final hash is the Merkle root. It's a fingerprint that represents every single transaction in that block.
And the amount of data this saves is, well, it's just mind-blowing. I mean, look at this. To prove your specific transaction is inside a block that has, say, 1,000 other transactions, you don't need to download the whole thing. All you need is your transaction and the few branch hashes that connect it all the way up to the final Merkle root. The difference is staggering. We're talking about going from 1/4 of a megabyte down to less than 500 bytes. It's an incredible diet.
This right here is the magic that makes mobile wallets possible. It's how your phone can get absolute mathematical proof that your payment is included in the blockchain without having to carry around the weight of that entire massive history. It's literally proof without the pounds.
But you knew there was a but, right? Like with pretty much everything, this amazing convenience comes at a price. There's a trade-off, a security trade-off specifically, and it's a really important one to wrap your head around.
So think about it. When your little mobile wallet asks for that tiny proof, who is it asking? It's asking one of the big, powerful computers on the network that has downloaded the entire blockchain. We call these full nodes. Your little wallet, it can't check everything by itself. It can't verify that the rules are being followed. It's basically putting its trust in that full node to tell it the truth. You have to trust that the server you're talking to isn't lying to you.
And that right there is the fundamental trade-off. It's a spectrum between security and convenience. On one end, you can run a full node yourself. It takes a lot of storage and bandwidth, but you get maximum security. You don't have to trust anyone because you verify everything yourself. On the other end, you use a lightweight wallet. It's super convenient, runs on your phone, but you are fundamentally outsourcing your trust to someone else's computer. So, let's recap where we are. We've built this incredible system where the past is basically set in stone. Those cryptographic links make it impossible for Lisa to rewrite history and erase her cookie payment. Awesome. But this whole thing still depends on Lisa to actually create the new blocks. So what stops her from just controlling the future? What's to stop her from just ignoring any payments she doesn't like? What stops her from just censoring the cafe completely so they can't get any payments at all? That question, who gets to decide what goes into the next block, is the next massive piece of this puzzle.